Have any suggestions, thoughts? What might be going on here? Yeah.
If these are neural networks, do the things with the number of parameters, does it relate to the, because on the top it says hidden layer size, but is that also the number of hidden layers?
Yeah, good question. So with these ones, are 1D. I think the only difference between this here and between this row and this row, I think there's one hidden layer in this, and we're just, it's kind of like the piecewise linear version. So it's one hidden layer, and we're just increasing the width of it. We're increasing the number of non-linearities in there. And so with these ones, so this says number of parameters because you know from having played with it now that for a neural network you've got width and depth, right? So essentially like the width times the depth is the number of parameters. So here, you can go and look this up. This is why it'll be your assignment because you have to figure out exactly what they mean here. But this will be something like the width times the depth. So it's probably getting deeper and deeper and possibly wider and wider as well. I don't know. Good question. Similar with this here as well. ResNet is a convolutional neural network, I think. So it has a parameter in there which controls the number of, has a hyperparameter which controls the number of parameters in each layer. Any other thoughts about this? Do you want to try and offer an explanation or something?
Is it because you're making it smoother as you increase the number of parameters?
Because you're making it smoother as you increase the number of parameters. Why are you making it? What are you making smoother?
Like, is it reducing the bias? Like, you're adding more of the lines?
Reducing. So, as we add the number of parameters, the thing we know from our toy example is, I'm increasing the model capacity, right? So it's like I'm getting smoother and smoother and smoother like this. So so that's something that's happening here. So that's definitely happening. So my output functions are getting smoother and smoother and smoother, I think, here as we go along here. And what else can I say? What am I not improving? From here onwards, what's not getting any better? Yeah. The error in the training set. So what does that mean? That means my number of classifications is not getting any better, right? I can't do any better on that. It's essentially the same with each of these. I can't get any better. I can't get any of my classifications better. So what has to be happening as I go further and further? Any improvements here must be coming kind of, it's not my training examples, not the distance of my model outputs to the training examples. They're fixed. They're right at this point. So anything that's getting better is happening between the training examples. You can think about to the 1D example, like to this, right? At this perfectly fit regime, everything here is exactly on, and so any improvements are happening between. Yeah, and I'm also getting smoother and smoother. So I should say, you can read the Prince chapter. There's a section called explanation here, and it's it starts off by saying the discovery of double descent is recent, unexpected, and somewhat puzzling, and that's in the textbook. It also says, so then there's some explanation that I'm going to summarize for you now, and it says this argument is plausible. It's a full stop there. It's not a question mark. Then later it's asked another question later on. It says the answer to this question is uncertain, but there are two likely possibilities. So this is pretty uncertain. So this is kind of speculative, but what you're saying is kind of right, I think, or at least it's what the expected explanation of this seems to be. So a couple of so the smoothness argument is this. So here's this example literally done. On our friend example again, and here is, and they've hacked this a little bit, so they've created a large unobserved gap here. the gap in the middle. And so, I can't remember, I think these are just two examples again, two separate examples. No, sorry, 6, 7, 8, 10, 50 hidden units, right. So with six hidden units, it's 6 parameters, this model's bad, and it's bad in this unobserved region here. 7 hidden units, at this point, see, I've got 1, 2, 3, 4, 5, 6 data points. So from here, I'm perfectly fitting my model in each of these. But you consider going from 6 to 7, the thing, because it's got less distance between each of my sort of nodes, my different piecewise bits, my piecewise linear bits are shorter, this gets smoother and smoother. That's the thing that we find. So, as I push past, observation number 1 is as I push past the perfectly fitting, the overfitting regime, what I get, additional capacity means additional smoothness. And so at least for this problem, that works, that's good. That's exactly what we want because I'm trying to predict a smooth function. It's a jump to say that smooth functions are necessarily good for MNIST, but that's something that's happening here. The other thing to say is the idea of regularisation here. So here are 3 functions that perfectly fit the training data, so they all have a loss of 0. So the loss of these is exactly the same. But, obviously this model is probably quite a bit better. So these have different amounts of regularisation, which I'm going to talk about in a sec, applied to them as well. So if you think about regularisation as being the number of a highly regularised function has fewer non-zero parameters, fewer non-zero terms in it. Well, this has got a lot of non-zero terms, and so it's got a lot of variance here. So this is a more highly regularised version of a more highly regularised function here. So essentially, the explanation that's given here, and this double descent phenomenon is very, very new. The term double descent was coined by Belkin in 2019. He demonstrated that test error decreases again in the over parameterized region. So this is only a few years old, right? This stuff. So in terms of open problems in machine learning, in deep learning and in AI that require math people, here's one right here. The textbook is not clear on what's going on here, but it's clear. It seems to be something to do with this smoothness, these ideas of smoothness and regularisation. That's it. So the quote here. If the modern regime of double descent is explained by increasing smoothness, then what exactly is encouraging this smoothness? The answer to this question is uncertain, but there's 2 likely possibilities. So possibly it's the initialization of the network. So that's how you initialize this thing to be this optimization. Second, the training algorithm may somehow prefer to converge to smooth functions. And so what does that mean? That means regularization. And so that's why the second part of this is all about regularization. So that's a very unsatisfactory answer to the question, but something for you all to explore. Questions, further comments on double descent? Okay, so the idea of that is as a segue into us talking about regularization. And so we've belaboured the point of capacity is smoothness, but regularization is something different. Who's done regularization in the stats course before? When I say regularization, who knows? Okay, a lot of people. Yeah, good. Thanks, Matt. That's great. Okay, so it doesn't matter so much if you've done this. I'll give you a crash course on what regularisation is soon. But the regularisation that you will have seen in stats courses that you've done at this university is very much traditional statistics. And the idea of it is including some explicit term in the loss function, in the cost function, that favours certain parameter choices. So if you've seen ridge regression, or if you've seen lasso L1, L2, regularisation, Tikhonov regularisation, if you're a math person, it means trying to damp parameters down to zero. So the first thing to say is that in deep learning, these are quotes from the Prince book again, we kind of mean any strategy that improves the generalisation, right? That improves this ability to predict unseen data. And what I'm going to show you for the last 20 minutes or something are a bunch of hacks that are very much fall into random things that seem to improve generalisation. Okay, but what's the traditional regularisation? It's something like this. So let's come back to this example from a polynomial regression from whatever pattern recognition of machine learning. So you can fit the data better by having more and more terms in here. And if you have too many terms, then you overfit. So how do you counter that? Well, you put a damping, you put a cost on having non-zero terms. So if this y here is a polynomial, that's like 9th order or 10th order or whatever it is, and so this weight vector has got 10 or 11 terms in it. Then basically I put an extra term in my cost function, I damp those down. So that's called ridge regression. If this was just an absolute value there without the squared, that would be lasso regression, and that's it. So basically, traditional regression would take that away. You basically try to damp these things down. And so if you increase this damping term, what this does is it explicitly forces you to be smoother and smoother, right? Because you are penalising having more and more terms. So if you make that as large as it can be, you get pretty close back to a flat line. You damp out everything, right? And you just have something that fits a model that's basically a straight line. Okay, so increase this regularisation parameter, and the nice thing is on the test data, you get improvements here. You actually get if you make this. If you regularise too much, you introduce biases again, and so this goes back up. But there's the idea is there's a nice plateau here. So that's explicit regularisation, traditional regularisation. The thing that I want to say to you in the context of this course, we've talked a lot about optimisation. Is that this traditional regularisation is just constrained optimisation. It's adding an extra constraint in an optimisation function. So this would be unconstrained optimisation here, and then I'm adding in extra terms. I mean, it's actually like a weak constraint. Maps one of these terms, but this really is adding in a weak constraint into optimisation. And there's a helpful picture for this as well. So let's imagine that I'm optimising some cost function. So it might be for a deep learning model, might be for linear regression, or whatever. So there's some cost surface. And let's say that if I just have a normal least squares type cost function, there's some minimum of this cost function somewhere off in space here. So there's some choice of parameters that optimally fits the data. By adding in an extra term that penalises the weight. Sorry, that's my penalty term, isn't it? Adding in a term that penalises the weights, you can think about, well, what minimises this cost function, ignoring the j, so that would be my least squares data bit. What would minimise this? Well, having no parameters at all would minimise that. So the minimum of that cost function will be here at 0, 0. So you can imagine if you just think about the parameters by themselves, right, the penalty term on the parameters, you're going to have some cost function that has a global minima at the origin. Yeah, right. So this is sort of coming up like this. This is trying to penalise having parameters. When my data comes in, when I'm actually trying to fit the data, I'm on somewhere off here. And so really what I'm doing when I'm trying to find some balance between fitting the data well, so being up here, and having small parameters, is I'm trying to be at the intersection of these 2 points, right? If I increase this, I guess it's alpha here. So alpha, the weighting that I put on my penalty term with the parameters, that's going to create level curves of this. I pick some alpha, right, and that's going to put me at some constraint here. And so hopefully you can see, what am I doing? Well, I'm really doing constraint optimization. I'm constraining myself to being on one of these circles, and then I'm finding what's the minimum of this cost function subject to the constraint that I'm on some circle here. And for those who are still awake by the last few weeks of optimization 3, if you did it when we were talking about the KKT, Tucker conditions, that was exactly the problem we were solving. Yeah, so regularisation can be interpreted as a constraint optimization problem. So, blah, optimization 3 notes. There we are. You remember all of that. Okay. So regularisation is this idea of improving generalisation. I could do it, you could do it, right, by doing lasso or ridge regression. So we've seen how you can write down a cost function for deep learning, right? I could add a term in that, a term exactly like this, and just penalise having too many parameters, right? That would be fine. If you think too much about, if you start to think about that, well now, if I'm in a constrained optimization regime, well, it was actually kind of painful to do constrained optimization. It was a lot more complex, right? So don't necessarily want to do constrained optimization. You know, there's another hack, there's another parameter that I've got to chuck into my cost function now to do this. So, you know, people don't actually necessarily do proper mathematics to do regularisation in these deep learning models. They actually do all these hacks. So I'll talk about a few of these. And then we'll do a little example. I'll drop out because it's kind of fun. So the first one, the machine learner is called early stopping. And early stopping is really cheating, because the idea of early stopping is that if you have some training set and some validation set, right? So you split your data into training and test, and you train your model and you check it. You check the accuracy on the validation set. Then yeah, you tend to get this thing where it plateaus, right? Where it plateaus if you keep training, and eventually it goes up. And if I increase the number of parameters, it goes up even worse, and it fits, and etc. etc. So instead of training it all the way up to here, you just say, well, I got a better result over here, so we'll just stop it and we'll take what the parameters were at that point. So that's just cheating, right? It's not really cheating, because you actually have a test set here as well that you truly haven't seen, and you train your model with a training set and a validation set, so you don't split your data into 80-20, you split it into 60-20-20, and you train on the 60%, and then you validate, you do your early stopping on the second 20%, and then you test it on truly unseen data. But it's pretty cheat-like. So that's a nice hacky way. To do it. And by the way, yeah, so let's see Goodfellow figure 7.4. I put that in there as a note to myself late last night because I wanted to show it to you. And you should do this stuff as well. So there's a whole chapter in this on different hacks for regularisation. But I wanted to show you this one. So the idea here of the early stopping is that you're minimising this cost function, right? Without a regularisation term, you're just trying to head towards this minimum here. The cost landscape has got lots of flat regions. We've talked about that. You're heading downhill using stochastic gradient descent. You know, if you're using momentum, there's sort of like a slow manifold that you're walking on. You're rolling downhill here. Early stopping says, well, instead of getting all the way down here, I'll just stop earlier, stop back here. And so that creates the effect of you being on some hypothetical level curve of another cost function that's penalising having non-zero parameters. So early stopping achieves the effect of an explicit regularising term. That's the cool thing about it. You don't really know what this is. You've given away being able to prove anything. You've given away having mathematics on this, but the effect is kind of the same. So that's nice. So early stopping. So there's lots of other things. So you can go into Goodfellow and you can read a bunch of different hacks. I don't actually remember what bagging and multitask learning are. It's kind of when you create, multitask learning is kind of when you create lots of different models. You have lots of different training data sets. So you create lots of different models and then you sort of average them together, and that has the same effect, has similar sorts of effect. There's another one called sparse representations. And so this is basically where you try and damp out, you try and have weights in your deep learned model. So you have weights that are sort of sparse, where lots of them are zero. And there are different ways to do this that link to compressive sensing. So you try to find low-dimensional models, sort of sparse models, and you achieve the same result there. There's dropout. I'll talk about dropout in a sec. We'll do that in a bit more detail. Here's early stopping actually implemented on our model, on our toy model here. So let's see. So I start off, so this is increasing the number of iterations up along this way. So we start off with a pretty bad model, right? High bias model. And then as I head downhill, doing my stochastic gradient descent up to 1,000 steps, 5,000 steps, I fit the data better and better and better until here after 200,000 steps I fit it really well. We should just step back and we should say which is the best model here. So the loss function is going down and down and down, of course. But I should actually stop somewhere back here, right? Because this model is a bit closer to the truth. So that's here. You can see early stopping. Maybe that model or maybe even that model was the better one to choose. And that's a way to do regularisation. Did I not? Yeah, let me skip to this and then we'll come back to dropout. Here's one more of these hacky examples. So this is input noise. And what input noise means is basically, I have this neural network. I've got these nodes. I'm feeding all of my data through these activation functions. What if I just added noise in at each of those activation functions as well? So instead of just doing a linear transform of my data and then chucking it through a nonlinear activation function, bunch of nonlinear activation functions, what if I added some noise as well? right? And so that's what this is doing. It's basically adding randomness to each of the nodes, to my input data, which gets carried through each of these nodes here. So what does that do? Just forces you to fit different training sets. I mean, I guess it's simulating taking different training data sets, and so increasing the variance bit here, and maybe that is helpful. Maybe this model, which has got more noise injected into my training data, has worked better here. The last one that I want to talk about is dropout. And so the idea of dropout, and I'll give you this in the assignment as well. The idea of dropout is, remember that every time you take a step, you are evaluating, you're evaluating something about this network. So you're evaluating outputs from this network. That's how you're taking, how you're calculating gradients and how you're stepping downhill. So dropout says, what if randomly, every time I pass data through this model, so every time I do a stochastic gradient descent step, every time I take a gradient, what if I switch off some of these nodes? So what if I just force, one of these nodes to be 0? So instead of passing x1 into the first nonlinear activation function, what if I just turn that off? Just force that to be 0. And you can do this in all these different ways, right? And so essentially you're adding more randomness in particular ways into the way that you step downhill. Why did somebody come up with this? I think probably because this is easy to implement on GPUs and stuff. It's probably easy to, with the architecture of how these things work, it's probably easy to zero out particular nodes rather than for any mathematical reason. But yeah, you're basically turning off, as you do this gradient descent, you're turning off bits of the network. And again, in our toy model, that's a nice thing to do because it maps exactly, turning off hidden units actually maps to turning off some of these parameters here. So if I turn off hidden unit 8 in this, 1, 2, we've got to see what's what, 1, 2, 3, 4, 5, 6, 7, 8, I think it turns it off there. So there's no result over here. The data we don't get outputs in this because I've only got one hidden unit. So what I'm trying to do is I'm trying to eliminate that sort of noisy bit here, that jump. If I do this lots of times, then eventually I find, well, it's a good idea to turn off this bit and this bit here. So I gradually, do lots of iterations. I'd randomly turn off bits of this model, and then eventually I find, it's a good idea to actually, it allows me to fit this stuff over here, fit this stuff well, has this regularizing effect. So it's a hacky thing that seems to work. We won't do an example. We'll do an example of that actually in a sec. I'll show you this we'll do this in PyTorch. So that's dropout. So hopefully what you can see, I think this is my last slide here, yes. This is a nice picture to just show you all of the different things that we can do. So regularization for deep learning people means something really broad. It means just trying to improve the performance of my model on unseen data, improve that generalization. So it doesn't mean the regularization that you do in statistics as only a small part of the picture. It's a very, very explicit thing to do. And then there are all these thousands of other hacks, right? Early stopping is the hackiest hack. Dropout. It's basically a way to make lots of different models, right? So the idea of having lots of is a way to generate an ensemble of lots of different models, and that sort of has this smoothing effect. It allows us to, tends to work. Applying noise is sort of similar. That's why it sort of goes here. But there's lots of other things that we can do as well. Yeah, I think where the state of the art is at with this is the two observations I sort of started this section off with, right? These things seem to work well, and they seem to generalize well. The deep learning models seem to generalize well because of a combination of two things. Because of smoothness, so because it's an architecture, a sort of general architecture that allows you to create quite smooth models. And you saw that with the double, you can see that with the double descent. And also, I think that's really closely tied to the idea that smoothness sort of has this regularising effect, and this wandering around the cost landscape has this regularising effect. It's all very tied to constrained optimisation. All of these things are basically hacky ways to do constrained optimisation. And what we're missing with all of this is sort of any sort of mathematical understanding of kind of what's going on here, or the mathematical theory of these things. That's the spot for you guys to get in on this. That's where the interesting questions are with all this. Questions on anything that I've said? Thoughts, comments, anything? Yeah.
So with these things, the idea seems to be generally to make the function that you're predicting closer to the true function. But given that you don't know the true function, is how you do that essentially just whether the testing data is good?
That's right. So for MNIST here, it might be pretty clear with my toy example. It's pretty clear with the toy example that smoothness is generally a sort of good idea in this unseen region here. But that was because of how I set it up, right? The big hack here, and the thing that this sort of talks about, is for MNIST, where the game is to take images, to take these grayscale images that are of size 800 or 700 or whatever, and predict a digit. It's not actually clear that smoothness should be desirable, right? It works, but it's not actually clear why. And that's a big question. Matt, yeah.
So I guess one of the things that's conceptually hard to get here is that in your picture, smoothness has a very clear meaning. That there is kind of a very easy picture.
Yep.
And when you're dealing with a landscape, it's not so obvious. Smoothness might have some other meaning. And to me, it's much more about having some sort of model, what's going on.
Yeah.
And smoothness is a very
sure.
Model.
Non-jumpy, I think, is probably a good is a better concept. So what does it mean to be smooth for MNIST? So it means that two of these 700 dimensional vectors that are labelled as the number 5 are close, and you can get between them in a non-jumpy way, right? You could sort of smoothly get between all of these things that are all called 5.
Another way might be in some space, things that are close together in the original vector space are close together in some sort of representation space.
Right, so you can kind of see, I think that does link back to this. How do you get from these points to these points? Well, this is a jumpy way to get between them. It's better to get between them in a sensible, direct way. You're doing that in a 700 dimensional space for MNIST or for any of these images. But it seems like a good idea that if I've got two numbers that are labelled 5, I shouldn't get between them. If I'm moving between two numbers that are labelled 5, I shouldn't go everywhere else in between them. Maybe, sort of smoothly deforming into the others. The other vector is a good idea. That's it. That's the intuition, but it is an intuition, right? I think this is probably why, if you start to look into some of the mechanics of how, like, the image generating AI things work. They all work on these like gradient flows and stuff, right? They're trying to. There is a sort of PDE type model going on under the hood here there that I don't really understand. So you're trying to flow these images into one another. This seems to be a useful concept, but it's not exactly clear why. But that's where the field seems to be at, to me at least. Other questions? Comments? Sorry to be so unsatisfying at the end of that. It does kind of peter out, because if you read this, that's actually where the theory peters out. All right, this has been a lot, so maybe we'll end up having an early minute. I want to leave you with a thing that you can do though. It's generalization week. Maybe I'll tap through this really quickly, and you can take a look at it. I do have an example of dropout here, so you can see how it works, and this will be useful. This is useful for the question I'm probably going to put in the assignment. The nice thing for you is that dropout seems like a complicated thing, but it's actually implemented very, very nicely and neatly in PyTorch. So I shouldn't have actually executed it. Here's a really simple. There we go. Really simple training and test data set. Right, so we're going to do linear regression with deep learning, which is a stupid thing to do, but that's all right. So we'll try and predict the training set, the testing set there, the yellow dots, from a model that will train on the purple dots. How will we do that? Obviously, the way to do this is with a neural network. So we'll take in our we've got NH is what the number of hidden layers, right? So we'll take in inputs here and pump it through a 2-layer neural network. So we'll do a linear transform, pump it through ReLU, do a linear transform, pump it through ReLU, do a linear transform again. So there's no softmax here, right? I'm not trying to predict. I'm not trying to predict a category that's got 10 things in it. I'm just trying to take X's and predict Y's. So we only need a linear layer to spit out of this. That's the only difference to what you've seen before. The nice thing about dropout is that it can be implemented really easily. So you do this dropout game every time you evaluate a gradient. Basically, this just means that after every linear layer, so every linear transformation that I do to my data, so I've taken 1 point and I've converted it into 100 from this. I'm going to take out 20% of those. I'm going to zero out 20% of the things once I've done that transformation. And we'll do that again, take out 20%, random 20%, and they get randomized each time. So that's all it's doing. It's really just a...
So do they put them back in after taking out 20%?
Yeah, no, so this is for, no, that's the wacky thing, right? And so you have a model here at the end that's got holes in it. And those holes have been randomly put in a way that causes the model to generalize well. So, right, so basically some of the parameters in this, if you think about this model as being a big transformation, it's got lots of multiplications and non-linearities in it, it's all composed, some of those things get forced to zero. And that's exactly regularisation. That's exactly what a regularisation does. So you can play with this. We train it forever and ever. Right, we're going to go through my my 50 data points here 1,000 times, just because we love to train things. And then this shows you progressively after each epoch what's going on here. So this is, I guess, you can see it training here. So the normal model is starting to fit the, gradually starts to fit the data more and more and more. Keeps going. You can see the model that's got dropout. It's got some of these parameters as being forced to be zero is a lot smoother here. Yeah, can keep. Guess we can stop there. So you can see that they're kind of pretty bad models, but hopefully you can see that this is the blue dashed one. Is a lot smoother here, and you should be able to. Have a think. But check how these generalise to the unseen data. Yeah, I guess you can see that there's the test losses there. So the loss for the model with dropout is a little bit lower. I'll let you play with this. Yeah, I'm going to stop there because I'm tired and you're probably tired too. Yeah, and then you play with this, and then the assignment will be to implement this on MNIST and see how it works.
What's dropout equal to? Oh, sorry, that's log loss, not dropout. Yeah, no worries. Never mind.
Yeah.
Yep.
All right.